Hello, welcome to another stream for Exercism Mechanical March. Tonight we're going to be streaming some C++. I already did a stream about C++ earlier this month, so I will try not to repeat what I said the last time. I gave an introduction to the language, and I also gave an introduction to the way that my environment is set up. Tonight, we're going to be trying another exercise, which is called binary search. So hopefully we're going to be seeing some of C++ uh, data structures in this exercise, namely the vector class. And if we have time, we're going to check out how to solve the exercise using generics, which in C++ is called templates. That's not a requirement of the exercise, but I thought that it might be a good exercise to showcase the capabilities of C++ generic classes and functions. So let's dive right in. As I mentioned the last time, if you check out the C++ track on Exercism, it has a lots of exercise. So tonight we'll be doing this one. So the binary search exercise, the goal of this exercise is to implement, as the name says, a binary search algorithm inside a data structure of sorted numbers. So for those of you who do not know what the binary search algorithm is, it is actually explained in the exercise later on. So basically, you get as input a sorted list of integers. It could be anything, but in this case, it'll be integers. And you have to find a specific integer. But since this list is sorted, you can actually implement a very fast algorithm for looking inside the sorted data. So the way it works is it's a divide and conquer algorithm. So you first start by looking at the middle element of the list and compare it to the one you're looking for. If it's the right element, then you found it. So you return its index inside the data structure. If it's not the element, then you compare it with the number that you have. If the number that you have is greater than the number that's inside the list, then you know that your number is later on in the list. So you eliminate the first half of the list. If and if the number that you have is smaller, then you eliminate the other half, the last half of the list. And you recursively go on and on and on, splitting the range by half every time until you either find the number that you're looking for or you end up with an empty range. And if you end up with an empty range, it means that the number that you have is not found inside the list. So in the exercise that we're going to show tonight, the way to implement this exercise is to you get a structure that's called a vector. I'll open up the test data here. So if we look at the first test, uh, it creates a structure called a vector from the standard library. A vector is a generic class. It's actually a template. That's how we call generics in C++. So it's templated with the int data type, meaning it's a vector of ints. Vector is just the name of the C++ class that is used to store contiguous list of data. So it's homogeneous data, meaning that every single element in a vector is of the same type. And it always stores the data contiguously in memory, meaning that as you insert data into a vector, if if the internal data structure sometime actually runs out of place in memory, it has to reallocate the memory somewhere else and copy the elements to the new memory spot. So the code creates a vector, and then it calls a function that we have yet to define, which is called binary search dot find. And our find method, our find function, sorry, must receive the vector, and 6 here is the element we're looking for. So the first test is simple. It's a vector of a single element that is actually the element we're looking for. And it is expected to receive the index inside the vector of the element. So since vector are zero based, the vector indexes are zero based, it is expected to return zero. So how do we solve this? Let's start by doing the exercise as if we are given the task of only supporting a vector of integers. So if I close this file and open up the binary search header file. So as I mentioned earlier, we have two files in C++. For code, usually we have a header file and a source file. So inside the header file, we're going to define the find function. So the find function, I'll just include some header files that we need in order to define that function. So vector is the file that includes the definition of the vector class, and cstddef actually includes the definition of a type named size t, which is an unsigned integer type that stores the size of the size of a data structure. It's actually dependent on your CPU architecture. So if you are in a 64-bit CPU, which most of people are nowadays, it's actually a 64-bit integer. And if you are on an old 32 bits architecture, then it's 32 bits, etc. So our method is named find, and it is expected to return a size t value, which will be the index. And it receives two things, as I mentioned earlier. The first parameter is the vector that contains the elements to parse and locate the found element in. So we're going to declare it like this, vector of int, let's call it elements. And then we get past an integer value to look for, which is the value to look for. Now, this signature here is actually valid in that it works, but it has a flaw. Uh, in C++, if you declare your parameters like I just did, they will get passed what is called by value. By value means that if you pass a complex object type like vector by value, the vector will actually be copied when it is passed to the function, which is a bit extraneous. We don't really need to copy the vector in our case because we're just looking to query the vector and not modify it in any way. So it ends up doing memory copying for nothing. So the proper way of doing that, of avoiding that, let's say, would be to pass the vector by reference. How do we do it? We do it by using the little and sign like this. So this declares that we want to receive a reference to a vector. And because we do not want to modify the vector, it is usually better to pass as a const reference. Const is a concept that exists in C++ and in some other programming languages, but not all of them. So for those of you who are not used to something like this, in C++, objects can be const or they can be non-const. If it's not if the word const, the keyword const is not used, then it's a non-const object. So if you have a const object, you can only call const methods on it, and you cannot modify its members, which in some languages who do not support the const the concept of const values. Usually you see like mutable and immutable types, like in Java or Kotlin or other programming languages like that. So if you want to pass an immutable data type, that means that the receiver will not be able to modify your data. but if you pass immutable data type, it will be able to modify it. So in C++, the usual way of doing that is to pass as const. So here, we're declaring the vector as a const reference to a vector of ints. So now that we have our signature, let's copy that over to the actual source file and implement the function. So I will just copy it here and open it up. So as I mentioned, the idea in order to do a proper binary search is to split the range in halves recursively. So what we'll do is that we will declare two variables, type size t, which is the type for the index inside the vector, and we will, when name one begin, initialize it at 0, and name another one end, which we will initialize at the number of elements inside the vector, which we can fetch by calling its size member. So here, at every step of the way, we're going to be looking at a specific range of integers between begin inclusive and end exclusive. So end points to one element past the range that we're looking for. So at every step of the way, what we want to do is we want to let's just here open up a for loop. Here what I'm doing is basically I'm doing an infinite for loop. I use two semicolons here, meaning that I have no condition to end the for loop. So this for loop will go on forever. But of course, we can break out of it, which we will do. So the first step is to calculate the midpoint of the range. So how do we do that? So we will define a value called middle index. And the middle index is we start from the beginning of the range and we add half of the range size. So we just do end minus begin divided by 2. Here, since we're dealing with integers, the division is actually an integer division, meaning it's automatically rounded down to the nearest integer when we get to the midpoint. So here, now we have our middle index. So all we have to do is fetch the integer that's at that index. So let's fetch the middle element. How do we do it? In the vector class, there's actually an overload of the square bracket operator, which allows us to fetch an element by, whoops, I wrote element, sorry, to fetch an element by using square brackets on our vector, just as if it was an array, a native array of the C++ language. So now we have our middle element, we have to compare it with the one we got. So we'll do if our middle element is equal to the one we're looking for, then yay, we won. So we just return the middle index, which is the value that we want. And now, if the middle element is actually higher than the one we're looking for, that means that the one we're looking for is before the middle element. So we want to divide the range in half by dropping the last half of the range. How do we do that? We say that the end of the range is now equal to the middle index. And else, if the middle element is actually smaller than to look for, then we have, if the middle element is less, then we drop the first half of the range. To do that, we set the beginning of the range to the middle index plus 1, because since begin is actually pointing at the first element of the range that we're including, then we always want to go past the middle element, the middle index that we have here. And now it works except for one thing. We did an infinite loop, so it kind of never breaks if we end up having an empty range, meaning that the begin and end values end up being the same, then it will not stop as we wish. So what we'll do is, instead of doing an infinite loop, we'll say while begin is smaller than the end. So while we have a range that contains actual items, we want to get inside the loop. One thing that we could simplify here is this last if is actually not needed, because if our middle element is not equal and is not greater, then it must be smaller, right? So we don't actually have to do that if, we just use the else here. Now, this code can end up in one of two states. Either we find the item we're looking for at some point and we reach this line, which will return the middle index, or we do not find the element we're looking for and we end up here at the end of the method. So what are we supposed to return when we reach the end without finding the element? That's a good question. And to know that, we're going to open up the tests. Here I will comment the if define the preprocessor definitions that prevent the rest of the tests from running. And if we look at the last tests, we see that what the test expects us to do is to throw an exception if the element is not found, and the exception must be of the type domain error from the standard library. I mentioned briefly how exceptions work in C++ during my last stream, so I will not be repeating everything, but basically it works the same way that it works in other programming languages like Java or any other. So you can throw an exception and then it will unwind the stack until it reaches the catch exception, which in our case will be in the test. So let's go back to our code. If we reach this point, we didn't find the index. So we'll just throw the domain error exception, signaling that the element was not found. Now there's an error because it doesn't know where the domain error class is. So I'll just include this header here called std accept, which is the header that includes the definition for the standard library exceptions. So here we have our implementation. I didn't spend a lot of time explaining everything in the algorithm, because the goal of the session is not really to present how to implement a binary search algorithm, but was to show how to do it in C++. So let's build this. So we're going to build and see if it passes all the tests. And it does. Here it says that all tests have passed. There were 11 tests and 11 of them were successful. So we have a working implementation. Now, what could we do to improve this situation? Well, first of all, what we could do is that in this implementation, we're using indexes to find the elements inside the vector and to define our ranges. But in C++, there's another way to do that, and it's to use what is called iterators. So iterators are objects, or are, let's say, objects, or can be pointers, but it's basically a pointer to a specific element inside a data structure. So vector, just like most data structures. Oh, sorry, I paused because there's a. Yeah. So just to answer the question, I'm looking at the chat as I speak to. So just to answer the question that I think is asked by looking for Amy in the chat, you are right that in C++, a reference is basically just a pointer. So when you specify a variable that is passed by reference, like I did here, in fact, what is done when you compile that is that it actually passes a pointer to the vector and not a, there's no real concept of a reference inside the compiler. Is if that's what your question is about, then you are correct. Now, there's a difference though in the C++ language in that if you write if you use a reference in your code, then it will not be possible to pass a null value. It's only possible if you use pointer types. So a reference can never be null. So if you look at the implementation of our code here, it's impossible for someone to call this code with a null reference to the vector. Whereas if I was to define it as a pointer to a vector, it would be possible to call the method with a null reference to the vector, and the method would the function. Sorry, I'm confused about methods and functions tonight. The function would have to check whether or not the pointer is valid. So to avoid that, we often use references because we want to simplify things and not risk having null references that could cause bugs because yeah, so that's the reason why I'm using a reference. But you are correct in the sense that if you pass if you declare it as the reference, basically everything that the only thing that the compiler is actually doing is actually passing a pointer by value. There's no real pass by reference here in the compiler. Okay, so back to our code. What I was talking about before that question was I was talking about iterators. So here I'll try to modify the code to use iterators instead of indexes. How do we do that? It's a convention in the standard library data structures that there are methods on every single data structures that are called begin and end, and they return iterators to the beginning of the range and one past the end of the range of the values contained in the data structure. So here, what I will do is I will write begin equals elements dot begin and end equals elements dot end. Now, if you notice here, the type of the variables that I'm declaring is auto. Auto is a keyword that basically tells the C++ compiler to infer what the type of their variable will be. Because in this case, the actual type is very long to type. It's actually std vector int dot dot iterator or const iterator in this case. So since it's very long and it's a bit tiresome to write, it's easier for us to actually use auto. And using auto actually makes a lot of sense, and it's a pretty good idea to use it a lot when you write C++, because when you use auto, the compiler infers the type for you, and it reduces the risk of you declaring the wrong type and perhaps triggering what is called an implicit conversion. Now, the goal of the stream tonight is not to talk about this, but let's just say that using auto is a good idea. There are other languages that have this concept, like Java has var and stuff like that. See, JavaScript also has, of course, the const, like let's say to declare an untyped const. Of course, JavaScript has no types. So, well, let's say that it does have types, but it's not a statically typed language because it's interpreted. And okay, so now we have our two iterators. So what we want to do is, while the begin iterator is different from the end iterator, and now when we want to find the middle point, what we do is here we'll switch this to auto and say let's call this element middle. The middle point is we start by the begin iterator, and we all end minus begin divided by 2. So this code here is actually works because vector is a data structure that is supports random access, meaning that you can actually access a specific element inside the vector, uh, and it's actually in constant time, meaning that for any index that you seek in a vector, it's the same order of magnitude to fetch it. So supporting random access means that the iterators can be manipulated as if they were indexes, let's say, and you can actually add a value to it to skip a number of spaces and stuff like that. To answer your question in the chat, yes, auto is basically a dynamic type inferred from the code next to it. So in my case, the begin value is inferred to be a const iterator of a vector because that's what the begin methods returns. So the compiler knows how to deal with this. There are certain situations when where the compiler cannot properly guess what the exact type is. It's rare, but it does exist. In which case, you sometimes have to type out the type explicitly, but most of the time, auto works. So now that we have our middle iterator, which is called middle, we will try to compare it. Let's delete this line, and we'll compare the element that is pointed to by this iterator to the element we're looking for. So here, the way to do it is actually to dereference the iterator using the star operator. So using star middle, it says dereference the iterator and return the element that it's pointing to. Now, if the element that it's pointing to is equal to the element we're looking for, we want to return the index. So how do we do that? We can actually measure the number of steps between the middle iterator and the beginning of the range. There's a function in the the standard library, that's called distance. Distance. And distance takes two iterators and returns the distance between them. So we want to compute the distance between the start of the vector and our middle iterator. And if we replace the rest, so it now if the rest of the code will be adapted using the same method. So if the element we're looking for is actually before the middle point, then we split the range. So here our end iterator becomes the middle point, and otherwise our begin iterator ends up being the middle point plus one. So here we have a way of dealing with the same. It's basically the same code. It works with iterators, and in C++, iterators, depending on the data structure that you have, they can be implemented in different ways. For the data structure vector, when you compile in release mode, the iterators are actually just pointers. So it's very fast because since you're just dealing with pointers, you're just doing pointer arithmetic, which is basically just like integer arithmetic, right? So you end up having a very efficient code. So if we compile this thing, let's see if we did everything right. So apparently we did. All the tests are still passing. Now, if we want to go a point further, what we did here is we implemented a method, a function that uses a loop to find the element that we're looking for. But there's another technique that we could have used. It's recursion. So what we could do is implement another function that returns that, let's say, call it find in. I'll just write auto here and I'll explain it later. So find in takes two iterators defining a range and the element that we're looking for. So we'll just do, here we have to we're going to take the beginning of the range, sorry, it's the end of the range and the element to look for. Here we have a function that is looking for the element in a specific range. And what we want to do is implement this function using recursion. So now this function has no return type. I used auto as the return type. So that I just did that to show you that it's actually possible to write functions that have automatically deduced return types. So what the compiler will do is it will infer the type of the return value of the function based on what is after the return statement, just like it does when it infers the type of a variable. Okay, so how do we do it? Here, it's just as if we are inside one part of the loop, right? So we find our middle point by calling begin, the same thing that is returned below. And then we do the same checks. So if the middle point is the element we're looking for, then we won. So we return the middle. So what we do is we return the iterator that points to the middle of the range. Otherwise, oops, if, just like before, if the middle point is greater than what we're looking for, what we want to do is call the function recursively by using just the first half of the range. So we're going to be returning find in, begin, middle, and to look for. And in the final else here, we want to find the element in the second half of the range. So we do return find in, middle plus one, and to look for. So this function performs a lookup in a specific part of the range. If it doesn't find the element, it actually just, oops, I missed the, there's an if missing here, sorry about that. Okay, so if it doesn't find the element, it calls itself recursively by splitting the range. So we're only missing one thing. It's to actually stop looking when we reach a point where the range is empty. So just before doing the find in the middle point, we're going to say if begin equals n, meaning we have an empty range, then we'll throw a domain error to identify that we didn't find the element. Now, we can now erase the content of our function and just use our recursive function here by first looking at the entire range. So this will result in one of two things. Either we get the iterator that points to the actual element that is the one that we're looking for, or an exception will be thrown. So since an exception is actually thrown when we didn't find the item, we can assume here that the IT iterator points to something that is valid. So we can return the same thing we did before and just calculate the distance between the beginning of the range and that iterator. So this solution here is the same thing as we did before, but using recursion. So let's build this and see if it works. Now there's a reason why I'm working towards a recursive solution, and I'll explain it. Okay, so all the tests are passing. So our recursive solution works. Sometimes using recursion makes a lot of sense because it's actually clearer than using loops. Not all the time, depends. But it's actually a very elegant way of solving some of the problems. For those of you who are used to think in terms of mathematics, recursion makes a lot of sense because in mathematics, some functions are actually defined recursively, like like factorial or some like that. Now, I've reached a point in the exercise that I wanted to reach is that I will try to show you C++ generics. Now, this actual exercise only uses vectors of integers. But in fact, the binary search algorithm uh, can be applied to any data that we can compare and check whether or not it's less than, greater than, or equal to something. Sorry, I will just pause to read the question in the chat. Okay, so the question looking for Amy is asking is a good question. Uh, the question is, do vectors enumerators lay out the items next to each other in memory? Yes, the vector type in the C++ standard library is basically just a dynamically allocated array underneath. So it always stores the items in contiguously in memory. So that's why using a vector is usually the best choice if you can if you don't reallocate the vector too much, it's actually very fast because lookups are in constant time at any point in the vector, since you can just index it whenever you want. And as I mentioned earlier, in a vector, the iterators are actually implemented just as pointers inside the vector. In release mode, usually when you compile in debug mode, they wrap the vectors inside objects to do bounds checking, just to make sure that you're not dereferencing an iterator that points to later in the vector. But usually in release mode, you don't get that to be really fast. So some other types of data structures like list do not implement contiguous storage. List is a linked list. The list type in the C++ standard library is a linked list. So point iterators to the list items are actually pointer to a specific node inside the list. So it when you increment or decrement an iterator in a list, you actually just follow along the node pointers. So it's not as it doesn't give you the same speed as a vector, but sometimes it's better to actually use something like a list. It's like in every other programming language, the actual data structure that you're using depends on your use case. It's known in C++. It's well known that usually in the standard library, the vector class is highly optimized because that's the most widely used type of data structure there is that is used. So usually it's a very good idea to try to use vector when you can. Okay, so here what I want to do is I want to modify my code to be able to use this find function on any type of vector. So what I will do is transform the function into a template. So the first step that I will do is cut this from the source file and paste it in the actual header file. I'm just missing, I think, the std accept header here. So there's a reason for that. I'll explain it later. So how do we define a generic function in C++? We use a keyword that is called template. And when you write a template, you actually provide it with parameters just like a function. So it works a bit like generic classes in other languages that support that, like Java or Kotlin or I don't know, whatever else. So in this case, when we want to specify that the template accepts any kind of type, we use the keyword type name. So here we'll define a template function that has two type parameters. Let's call the first one V. Actually, it has only one. Okay, so it has only one, sorry. I'm a bit mistaken. So v is actually the type of the vector that we'll receive. So here, when I declare my function, what I want to do is instead of specifying vector of int, I will just write v. So a template is an apt keyword for it because in C++, template functions are really just that. They're just templates. So basically, you're telling the compiler, here's a template for a function that is called find that can be applied to any type of vector of a data structure. So if you want to use it, you have to what is called specialize it. So when you call the function with a concrete data type like vector of int, what the compiler does, it actually compiles a specialized version of your function where it just replaces the type names here with the actual type that you passed in and compiles that function. So here, I will change both of my functions to be templates. So the first function actually receives a vector, a type named v, which is actually the type of the container. I could have called it c. Let's call it c, just to emphasize that it's not necessarily a vector. It's just any container. And then the find in function doesn't receive the actual container. It just receives the iterators. So I will just write it as a template that has a type parameter that's called it with a usually it's a convention to write template type name parameters with the uppercase, starting with an uppercase letter. So basically we're just using camel case here. It's just to distinguish between what is a type name inside the template with the concrete types, which are all lowercase in the C++ standard library. So here, I will replace the iterator references with the actual type name it. And now there's, I see why what I'm missing here. So here we find a type name for the container in the find function, but we didn't apply a type name for the element that we're looking for, which is a mistake because it's not necessarily a container of ints, right? So let's add another type name called t, and instead of receiving an int, we will receive a const reference to a t element. Now, why are we using a const reference here? If we were to receive ints, then we could just use t and not a const reference to a t value. But since this is a generic function, we might be called with object types that are complex. And if we don't pass it by reference, then we're going to be called by value and incur an object copy. And in some cases, it will actually be impossible to call the code because some objects cannot be copied. Sorry, I'm just taking a bit of water. Okay, so in the find in function, we actually want to do the same thing and use a type named t for the element that we're receiving. So do we have to modify anything else? Actually, we don't, because everything else is actually, since we're writing a template, the actual code that's inside the template will not be fully compiled until the template is specialized, with an actual concrete type. This is different from most other languages that implement generics, because in most other languages like Java, in order to use a generic, you actually have to specify, the compiler compiles the generic method or the generic function, let's say, and it actually has to know a lot of things about the types that you're dealing with. So if we look at the find function here, we see that it receives a const reference to a container and actually calls methods called begin an end on that container. But when we declared the type name C, we did not say anything about that type. We didn't mention to the compiler that C actually has a method called begin or end. We just said, oh, it's any type. So how does that work? In C++, when you compile a template, it just does a very basic check to make sure that your code is actually legal, but it doesn't actually compile the function uh, completely, and it doesn't interpret the function calls that you're making. So it will only do that once you specialize the template. So if we look at the tests, now here, because the find is a generic function, it will accept the vector of ints. It will accept the int element to look for. And if we compile our code and run it, we should be uh, able to pass all the tests. Now, and we do. So everything works. So as you can see in C++, when you declare a template, it's actually very flexible. So you do not need to specify to the compiler pretty much nothing about the type that is actually passed in. You don't have to specify what type of methods it has. You don't even have to specify that the specific type of iterator can be incremented, or whether or not the actual elements can be compared to one another. The compiler will just do that when you try to use the function. Now, this being said, there's actually a bit of a problem with our code here, is that it in it it will only work if we're using it with a container that has random access iterators, meaning that the iterators you will be able to increment the iterator by a specific amount of steps, and etc., etc. So this code here that I'm highlighting, when we calculate the middle point, this will only work if we if the iterators support random access, meaning that it has a plus operator that takes an int, etc. So in order to be more generic and support more container types, we could change that code to actually use something that would allow us to work even if the iterators do not support random access. So how do we do that? We start by copying the middle point here, and now we're going to use a function that is called a function from the standard library. It's called advance. So advance takes two arguments. The first argument is the iterator that we want to move, and the second argument is the offset that we want to move it for, move it by. Sorry. So here we're going to calculate the distance, as we did before, between the beginning and the end of the range, divided by 2, and advance our middle point this way. So this code here is actually the same thing as we wrote before, but if we're dealing with iterators that do not support random access, it will work differently, because in C++, it's possible to do something that is called partial template specialization, meaning that it's possible to write a different implementation of a template for different types that share a specific characteristic. And the advanced method has that. So if you call the advanced method with a random access iterator, it will just do plus, like we did before. But if we call it with an iterator type that doesn't support random access, meaning that the only thing that it supports is incrementing by 1 or decrementing by 1, then what advanced does, it does a loop where it increments the iterator by 1 a specific number of times. So this is just more generic. It will work with more data types. So for example, this code here would work even if the container type was a list, which is a linked list. whereas the previous version would not work that way. It would not have worked if we were to pass it a list. Now we do not have a specific test for that, but it's just it's just true. So if we compile it again, we see that we're still passing all the tests. So now, one last thing before we conclude this is why did I copy the functions inside the header file before I wrote templates? The function declaration was in the header file, and the function definitions were in the source file, like we usually do in C++. But when you're using templates, it doesn't work because the compiler has to see the entire template definition in order to be able to specialize it for a specific concrete type. So here we have to include our entire function definitions inside the header file. Otherwise, we will not be able to use them. If we were to move these to the source file, it would not compile because then the compiler would not be able to see the implementation. So if when the tests call it with a concrete type like vector of int, it would not be able to know how to compile that using vector of int as the type, etc., etc., etc. So there you have it. Now we've solved this exercise using multiple ways. First, using a loop and indexes. Then we solved it using a loop and iterators. Next, we did a recursive solution, and now we're doing a recursive solution that's actually a generic function using templates. So if you look inside the standard library, it actually has a method called binary find or binary search. I'm not entirely sure which it is called. That actually does exactly that. You pass it two iterators pointing to the beginning and end of a range. The range must be sorted, and you pass it an element to look for, and it returns the iterator that that points to the element, or if it doesn't find the element, points to the end of the range. So that's something that I didn't mention, but usually in the standard library, when you call a function with iterators and for some reason it doesn't find an element, the convention is not to throw exceptions because that's would be very impractical to catch all the time. So the convention is to return an iterator pointing to the end of the range, which is not a valid iterator to the reference, but it does allow you to detect that you've reached the end of the range and thus the element is not found. So yeah, so this code here could actually be used in any different type of the only thing that could be changed more, it would be the comparison operators here, because in modern C++, there's a new comparison operator that allows you to do, basically it allows you to compare two elements and determine whether it's less than, greater than, or equal to in a single call. Whereas what we're doing here is that we're first using equal, so we'll equal here to know if the element is equal to the middle point, and if it's not, we're doing a greater than comparison. So we're comparing it again. So if the comparison operators were complex and costly, that would lead us to do two comparisons. Whereas in modern C++, with the operator that does it in a single call, could be faster. But I didn't show that tonight because I'm not entirely sure that exercisms exercises are equipped to deal with that version of the C++ standard yet. So, but if you're interested, you can look that up. Which leads me to something else that I wanted to mention. So I will go back here. I wanted to mention something that I didn't mention in my last C++ stream. Two very useful websites. If you want to learn C++ and you need references, there are two very good websites that I often consult as reference. The first one is called cppreference.com. It's a very let's say, not very nice looking website. It's not nothing snazzy in terms of interface, but it's very complete. It's a very good reference to the standard C++ library, and actually has also a reference to the C++ language features too, which is very good. So if you're, let's say you're coding in C++, and you're not sure of what the actual name for a method of the vector class is, or whether or not the basic string type supports fine or anything like that, you can just look it up on CPP reference. It has a search feature. It actually has a way of presenting it that's separated by libraries. So it's a bit on the technical side. So when you read definitions on the CPP reference website, it often has a very, let's say, standard friendly way of saying things, which can sometimes be a bit daunting, but you get used to it. Okay, thank you. Somebody in chat mentions that the Exercism uses C++ 17. So basically, the C++ language, just a bit of history for those who don't know what that means. The C++ language evolves like any other language, but contrarily to some other languages, which are basically controlled by a single entity or group, the C++ language actually has standards determined by committee. So there's a C++ standard committee that accepts submissions to new inclusions in the language and in the standard library, and it publishes new versions of the C++ language every 3 years. So that started in 2011 with C++ 11, and every 3 years we had a new version of the C++ standard. So we have a C++ 11, 14, 17, C++ 20 in 2020, and now they're working on C++23, which I believe is not yet finalized. So even though we are actually in 2023 and we're up to C++20 now, it's not entirely clear because whether or not we can use these new features yet, because the standard committee publishes uh, new versions of the standard, but it doesn't actually implement the standard. So when the new version of the standard comes out, it actually has to be implemented by the various compilers, the various C++ compilers that exist. Usually, compiler vendors are pretty fast. They start working on new version of the standard even before they are released, so that they are up to speed when the standard is finalized. But it sometimes does happen that some features are very hard to implement and actually are only released a bit later than the standard is actually published. So yeah, as looking for any mentions, we could probably update this to C++20. It would probably work. Okay. So the second website that I wanted to mention is actually not a reference website. It's the C++ core guidelines. So the C++ core guidelines is a set of guidelines that basically present good ideas of how to write proper C++. It's it's not really a style guide. Lots of programming languages have style guides, like let's say Java or Ruby or other languages. But the core guidelines, it's sometimes a style guide, but it's mostly a guide of good ideas to how to write secure, proper, and performance C++, so that to avoid like passing parameter by values when they incur copy, how to protect against buffer overruns, how to protect against unallocated the missing freeing of memory and stuff like that. So it would advise you not to use new and delete, but instead to use unique PTR and shared PTR, which are C++ standard library classes to wrap raw pointers. So the guidelines are maintained by two people, Bjarn Strustrup. I don't know if I'm pronouncing it properly. Sorry. Bjarn Strustrup is actually the creator of the C++ language, and Herb Sutter is a very old contributor to the C++ language. So they maintain the document, but not all of the document is actually written by those. There are contributors that have given ideas over time. So it's a good idea to take a look at this if you're serious about writing C++, if you're serious about writing good C++. Uh, uh, it's a pretty good idea to actually have a look at this and at least skim parts of it. It gives very good tips. I'm a mentor in the C++ track on Exercism, and I often reference the C++ core guidelines when I do mentoring. So it's mentioned in the chat that the maintainers want to use the latest version of C++. Oh, okay. So C++ 17 is probably the most recent version that is supported by the mainstream compilers that are shipped with the current distributions. Yeah, Herb Sutter is a very important person in the. So I didn't know he was the chair of the ISO C++ committee. That's a good thing to know. I didn't know that, but I knew that he was a very important person in the C++ committee, in the C++ community. Sorry. So anyway, that's about everything that I wanted to present tonight. So if you have any parting questions, I'm still looking at the chat, but otherwise, that would conclude my stream for tonight. I will perhaps try to do another stream if I can to showcase perhaps an exercise of that is using memory pointers. But I don't know if I'll have more time during the month, but it's possible. I will try to do another stream. So thank you for joining me tonight. Thank you for the good questions in chat, and let's I will try to see you in other streams. There are other people streaming other languages too. I know that there's somebody else has actually did a C++ stream in this month so far, and there are very cool streams for other languages like Rust, which is a very interesting language to know about for people who do C++ because it's a systems programming language that aims to be more secure than C++. Whether or not it is, I don't know because I don't know the Rust language. So, but if you want to learn Rust, there are lots of cool videos to see too. And we'll see you next time. So, thank you for joining me tonight and have fun. Bye.